Okay, so today we're going to be describing how to solve this equation and code it out sequentially. So for the following network, calculate the water flows through each pipe segment and the net flow in and out of the source, node 0, and the sink, node 4. So we're going to have to import numpy as np, which allows us to import pi, logarithm, all sorts of fun stuff. And then from scipy.optimize import Newton. Newton allows us to find the zero of a function and with an initial guess, and the guess will be flow rate eventually, but we'll solve that out later. So now we can do the main equation, which I'm just going to hashtag it up here so we can reference it. So it's going to be delta head. Make a function for delta head. Plus k, which is the fitting number or constant, plus 4 times f times d over L over diameter, length of the pipe over diameter of the pipe, times velocity squared divided by 2, all divided by gravity, right? Because we can switch around the main equation with the change in altitudes. You can divide everything by g. So now we can just write an equation out for delta head. D head, it's got to take in the parameters of flow rate. This flow rate will be used to solve for velocity because we don't have any numbers for velocity. L, D, and relative roughness. Okay, so now we can start writing out these equations. Q is equal to A is equal to flow rate, or solve for V actually. So V is equal to Q over A. And area is just of the pipe, so it's going to be pi r squared. Numpy dot pi times an r. We don't have a radius, but we do have a diameter, so it can be diameter divided by 2, all squared. So that's velocity. Now we can solve for Reynolds number also, which is equal to Q times V times, it's actually rho, got some of those off there, it's rho VD over mu. And then we're going to return this equation up here. And it's going to be negative since, I forgot to write this in, it's all equal to 0, so we can switch it up to the other side. And so we're missing a few numbers that we don't know. We know what K is going to be, we know what L is going to be, we know what D is going to be. We solved out for V, and gravity is just a constant. So we don't know what rho is. Well, we do know what it is, but it's not, the coding doesn't know what rho is. And rho is just the density of water, so 1e to the third. Mu is equal to 1e to the negative third. And then anything else we need to put in there? Yeah, ED is equal to 1 e to the negative third also, right? That number. E is equal to 0.1. And I think that's about all we need right now. Oh, and gravity. G is equal to, yeah, 9.81. Gotta know that one. However, we don't know what F is. So F is the Darcy friction factor, I believe. We'll use the Churchill equation, hashtag Churchill, to solve for it. And it will take in Reynolds number, relative roughness, and yeah, we'll solve it out. So there's going to be these two components we'll solve out for. And we'll use this equation right here, Churchill equation. All right, so A is equal to 2.457 logarithm. 457 times beta log 1 divided by 7 divided by Reynolds number. And we're just going to plug this all in to the 0.9. Put parentheses around all of it. Plus 0.27 times ED. It's kind of weird. It's not allowing me to do that. I'd very much like to put it in the center. There we go. Now I may or may not have the correct amount there to make it all under to the 16th, all right? Yeah, 0.27, 7 over Reynolds to the 9th, plus 0.27 times relative roughness. Okay, now B is equal to just 37530 divided by Reynolds number. All right, now we can just return 2 times all of it raised to 1 over 12th. Uh, 8 over Reynolds number to the 12th. 8 over plus 1 over a certain number, A plus B to the 1.5. All right. So I'm going to check my parentheses here. Okay. C. And just to make sure it works, I'm going to put in 1, 1.5, say 10. D is going to be 0.1, and then ED is going to be 1 e to the negative third. What did I do wrong here? Oh, V, capital, did I put a capital V instead of a regular V? How many times did I put that? Unsupported operand. Oh, F. Yeah. Forgot to put back in the function. It can be RE and ED for that. Is that the last F? Yeah, there we go. So that's the drop. We're going to have to make a flow rate equation, which takes in a given delta head, K value for fitting, L value for length, D value for diameter, and relative roughness. And we're going to have to do a Q guess, which is going to be the guessed flow rate in order to find the fitting equation or a fitting constant F. As we see here, V is equal to Q over A. So if we just rearrange that, we can get A times V. V is equal to, I'm going to rearrange this whole thing here now. Negative delta head divided by all of that. Murphy dot NP dot square root of it all times 2 times G. I believe that's the correct form of it rearranged. We don't know F because for the Newtonian equation we'll be solving for F, so we have to put in a guess for F as 0.01. However, we ran into a problem here where it's negative, and when you put a negative into a square root, it's no bueno. So we will have to correct for that by making it absolute, and we'll correct for it later. NP dot absolute of delta head. Yeah, now we can D head absolute. Same thing up here with this one too. We have to account for Reynolds number being has to be positive. So we're going to do D absolute of it all. And then it's going to return, I don't need to put that around there. np dot sign q, and then I'll correct for the flow rate. Yeah. Now we can do our function for the F20 with the first one delta. Wait, no, don't need delta head in this. It's just going to be Q. And it's going to return the 0 of the function with d head, this equation. In order to make these two equal the same, you have to divide or minus d head absolute. So it'll find the 0 of that. And then it will return now we got to find the resulting flow rate. The resulting flow rate is going to be using the Newton function that we talked about before, which is going to find the 0 of the F0 equation. So I named it that. Right. And then our x0 here, or guess, is going to be Q guess. And then it's going to return resulting flow, but since we put some absolutes in there, we're going to have to do correct for that. np.sign of d head or delta head. Okay. Now we gotta do pipes up here. And yeah, np.array of all that. It's gonna equal pipes. Yep, there we go. So now we can start listing off a couple things through it. Z values, which is the altitudes. Z nodes is equal to np.array .30, right? So that's the first one. And then for now it's 0 for the rest of them. And then we got our external nodes. Which is equal to pipes. Actually, no. It's just equal to numpy.array of 2e to the 5th and 0. External p. And then we got our external nodes, which is going to equal np.array of, I believe it's, first one is going to be 0, and the last one is going to be 4. We got 4 nodes. And then we got to determine our from nodes, which is going to equal this first column here. So it's equal to pipes. This, and since index is going to be the first one is 0 in an index. However, this is a integer, so do dot as type, that would be dot int 32, invalid syntax. What does it want here? There we go. Just didn't like that extra parentheses. Okay, and then 2 nodes is equal to pipes, and then it's going to be the first one there, and it's going to be the same thing as up there as type numpy dot int 32. Okay, that all checks out. Now we can start listing off a couple of other things we got up here, such as the lengths of the pipe is equal to pipes column all the way down, or rows all the way down, and it's going to be the third column, so 3, and we don't need an as type integer because it's already converted, so that's good. And then we need our k values. K is equal to pipes dot fourth column. All right. Now we need to make a shape for our nodes. So number nodes, or n pipes, is equal to pipe dot shape. We'll find the shape of that array up there of tuple of array dimensions 0. Tuple is not called. There we go. Let's mix those up. Now we need pipe D. We'll just assign, since we have the shape of it now, each one of the pipes will be assigned a diameter. Now we could just like go through it entirely and say 0.1, 0.1, 0.1, 0.1, but it would be a lot easier and a lot cleaner if we just incorporated it into the array itself using the numpy.full action. So numpy.full, the number of pipes that are there, and then fill value is going to be the diameter, which we already have up top. Now we can also do that for the relative softness. So MP dot full end pipes ED. All right. Now we can do a function for calculating flows with an input of heads available, which heads will come from the amount of nodes, which we can just take the maximum amount because we don't know how many nodes there are going to be. So in this case, it's just kind of a nice schedule. Nodes equal MP dot max of pipes, and then we can use any of them, but I'm just going to say 2 pipes, so that's going to be the maximum, right? Because yeah, and then dot as type np dot int 32, right? Because it needs to be converted from an integer. Okay, and then heads is equal to the zeros, np dot 0 of the n nodes available. Okay, now we got that. Heads should be 4. Okay, well we only got 4, but that's because it's index, so you have to add 1. There we go. Now we have the proper amount. Okay, now we can go about solving our problem and go about our day. Calculating this stuff for I in range of number of pipes. Okay, basically it's just going to run down the amount of pipes we have here, so that's going to be 6 pipes. Oops, and always check. Yeah, 6 pipes. Okay. For I in range of n pipes, we're going to use the flows equation, or the flow equation we had from before, and we need delta head. So how do we solve for delta head with an array involved? Well, delta head is just the difference between the 2 pipe and the from pipe. So heads of the 2 nodes, no, 2 nodes, index of I, and then minus heads of the just gonna do this from nodes. Flows I is equal to, let me get down to it, delta head, K is going to be, we already marked it up there, the 3rd row, KI, and then the lengths I, D is going to be piped I, and then AT is going to be PD I. Yeah. And then it's gonna return flows. Well, the problem is that for flows, we have to zero it out just like we did with the heads. So flows is equal to np dot zeros with the amount of pipes. So we'll get 6 of them. Calculating the net flow rate. Taking in the flows. Granted that net Q, just like the rest, will equal it will equal zeros. The number of pipes available. Now we do numpy dot add at right, if it's going from a node, it's going to be losing flow, and then np.add at net q when it's going to a node, it's going to be adding. So yeah, it's just going to be saying like from a node, it's going to lose flow rate, and then to a node, it's going to gain flow rate. Now we're just going to do net q internal, taking into effect internal p. Now we're going to find the equation for heads for the internal nodes. Nodes, which is equal to internal P divided by rho divided by G, right? That's the equation for the head, plus Z. Did I say capital Z or okay, Z from heads? Plus Z nodes. Internal to just return calc net q of this right here. So it'll take the input of heads up here, come down, given internal nodes. Then we need to find how many internal nodes there are. Internal nodes is equal to total number of nodes. So we'll put it all into a list. And then the range of n nodes minus set, new empty set of the external nodes. Yep. However, I'm going to move this up to there we go. Make it a little more clean. Now we can and then find a root afterwards. So internal head guess is going to be equal to np.mean of the, I'll write it out now and then explain it, of the external nodes. Yeah, because internal equals external, what goes in goes out, and yeah, it's a good guess to start out with. We'll find out later. And then internal p guess is equal to janitor's house. Is equal to the equation for head is equal to p over, I'm just going to write it out, p over rho over g plus internal head guess minus z nodes internal nodes times rho g the entirety of it. Rho's not defined. Oh. And capital R. And use the root function, which we have to define up here. It's another SciPy to optimize. Write it down. Yeah, it's missing the function, obviously. Which is going to be net flow internally and the internal pressure, yes. And then let's do result.x. Failed to converge 50 iterations. So what's it missing? It's just going to run through and never converge. So I think the problem here is that there's just D head is not accounting for if the head gets really, really small, so it's going to keep on running through, won't be able to find anything. So we're going to have to set a limit for that. So if D head absolute is less than 1e to negative 1, return 0. Okay. Yeah, that should help it out. Now we do calculated flows is just going to equal calc flows heads up here with all the guesses in. So we're going to print out all of the numbers for I in range of n pipes. And it's just going to be a print statement from or f. I think it's just going to be inputting numbers from. So it's going to be an integer pipes, and it's going to be 1i. So it's going to be 1i. That's going to be the first row, the first column, or that one's I is the column. Yeah, it's just going to run down the columns. 2 pipe is going to equal int pipes 0 I, and then flows are going to equal the same thing with all this, except int calculated flows I. Index 4 is out of bounds. Okay, so for axis 1 with size 4. There we go. So we run it all. I'm just gonna restart and run all. Sometimes it messes up that way, and I can find any sort of problems like that. It's supposed to be capital N. Result is not defined. Yeah, that's supposed to. That's still 0. Flows 0. Yeah, I think that's a little too large of a number. still not going to cut it. All right, so look at here. So calculated flows takes in outflows heads. So has something to do with. It's still E head. Say like one. Well, I'm just gonna see if it works. Alright, so that outputs. Not gonna be that big of a change in head, obviously, as it wasn't that much flow. Absolute delta head. GL. Absolute. Casing. It's still equal to. Okay, so that's equal to 0. What are heads equal to? That's because we've only calculated the internal heads, not the external heads, and the internal heads pulls from the external heads to flow out. So of course it's going to be 0 because it hasn't received any of the flow from the external heads. So we gotta calculate the external heads. Heads external, it's gonna be brackets, because it's an array, is equal to the equation for heads. So for delta head at least, external P divided by rho times G plus Z nodes, right? Because it's gonna be pressure over rho G plus nodes, or plus Z, and Z is not divided by G anymore because or it's not multiplied by G anymore because we divided everything by G. So that's why it's over here on the external P. External nodes. Okay. That should do something, yeah. Hey, there we go. Yeah, calculate net flow because that's the final thing we gotta find. Calculated net Q is equal to calc net Q, and the flows is going to be through each one of the heads. And pressure is going to have to be zeroed out. It's going to be NP dot zeros. Yeah, NP dot zeros of zooming out n nodes. Pressure, most external nodes is equal to, we already know the external pressure. That was, yeah, already said. Pressure internal nodes is equal to result dot x. Usually solve for it up here. Take the mean and guessing it through a root to solve the function with a guess using the root function, which is a handy dandy tool. Now I'm going to just say for I in range of n nodes, because we're just going to run through all the nodes. Take this print function up here and then place it on down there. But I'm just gonna say that was a lot of nodes. It's just gonna be I. Just gonna run through each one of them, and then, right, yeah, 1, 2, 3, 4 nodes. And then pressure is just going to equal pressure I. Yep. And then Z is going to equal Z nodes through I. Bingo. Y is Z nodes equal to 0 throughout it. Is there a reason for that? Of course there's a reason for it. Let's do all equals 0. And then we have node pressure Z. So last thing we have to know is calculated net flow. Net flow is going to equal so this is, the Z is independent, so it has to be something up here that I got wrong. seconds are all good, but the z is wrong. Okay, control find. I'm gonna get messy with this. Z's. Z node, Z zeros. Z is equal to Z nodes I, which makes sense. So it's just gonna run through each one of these, right? Yeah. No, it's totally fine. Okay, well, that's the final, that's it, I guess. That's the entirety of it. All right.